Okay, so this class, we're going to pick up again with another data structure that's designed to answer questions about a tree. So last class, we saw the lowest common ancestor data structure, which could, if you give me 2 nodes in a tree, it will tell you the node of maximum depth, which is an ancestor of those 2 nodes. Here's another problem on trees that seems to be important and has lots of applications, and it looks kind of similar. It's called the level-ancestor problem. And well, it's still the queries. There's 2 parameters. There's a node U, and instead of a second node, there's a depth D. And what you're supposed to do with this query is tell me the ancestor of U, which has depth D. And so remember, the depth of a node is the length of the path from the root to that node. So for example, here's a node of depth 1. And so this assumes then, so the ancestors of U all have the same depth as U or smaller depth. They can't have greater depth. If they have greater depth, they're either not ancestors or they're descendants. So this assumes that the query depth is less than or equal to the depth of U. Otherwise, the query doesn't make sense. Okay, so you give me U and D, and the data structure is supposed to give you a pointer or the name of the node, which is an ancestor of U. So it's on the path from U to the root, and its distance from the root is D. Okay. That's clear what the problem is. And it's a static problem. You're given the tree T once and for all. You pre-process it so that you can answer these queries quickly. All right. So, one thing you can, and as usual, we'll talk about solutions because we're going to be, to solve this, we'll present a number of different solutions. And we'll always give 2 parameters, which is space and query time. So we'll write our solutions like this. This tells us how much space the data structure takes. This tells us the query time. And actually, in all circumstances, the time to build the data structure will be the same as the space. So that's, we won't distinguish. So this is also pre-processing time. And there's only maybe 1 or 2 places where I'll have to mention something about the algorithm for building it. Mostly it'll be straightforward. All right. So let's say the first thing we want is a data structure that uses O of n squared space and constant query time. How do we get a data structure like that? So we use a table, and it's indexed by what? Okay, so use a table, and that will be indexed by nodes of T and depths. So the nodes of T, well, I didn't say it, but we sort of always assume that the size of the problem is n. So n is the number of nodes of T. So there'll be n different nodes. And we can just call those nodes 1, 2, 3, 4, 5 up to n if we like, just so we can think of them as integers. And then the possible depths that you can ask me about. So what are the possible values of this depth? Nothing, we know nothing about the tree. It's the data. It was given to us.
Starts from 0?
Mm-hmm. So it can't be smaller than 0, the depth. The root has depth 0, for instance, because the shortest path from the root to itself has length 0. What's the maximum depth? So it's in fact n minus 1. So even if the whole thing was a list, so there was no branching at all in the tree, the root would have depth 0, and the last node at the bottom of that thing would have depth n minus 1. All right, so that's n nodes of t and n possible values for the depth. That's a n by n table, so it's going to have space n squared. And for each entry in that table, so on the, let's say the rows are indexed by u, columns are indexed by depth or d, and for each entry in that table, you just store the answer. Okay, so what is the level ancestor, the ancestor of u at depth d? You store that there. And we did this last time when we were studying lowest common ancestors. What we will do, just to be precise about what's stored in this table, we don't really want it to depend on whatever the names of the nodes are in your tree. So anytime you give me a tree, I will just find some way to name it consistently, maybe in depth first order, like and then the answer that's stored here will be the depth first name of that node in the tree. Okay. So that way the answers here, instead of being node names, we don't know what they are, they'll always just be integers between 1 and n. And they'll really just depend on the shape of the tree and where really just the shape of the tree. So the whole table you can tell just by looking at the shape of the tree rather than what the names of the nodes are in the tree. Okay, so that's easy. Let's remember it. Let's try something a little harder. How about n log n space and O of log n query time? So we'll be a little bit slower with the queries, but we'll use much less space. Yep. What? Okay, so we kind of saw a trick like that sounds for when we were doing lowest common ancestors, or more specifically for range minima, which we had reduced lowest common ancestors to. There's this trick of for each of these things, for each node, store log n different values, where somehow the values are things that correspond to things that are getting further and further away. So for each node u, and let's say of depth, well, let's just say each node u, store the answers to the level ancestor query of U and depth of U minus 2 to the L for each L in 0, 1, 2, up to log n. Some of these won't make sense because you'll get a negative number here, but just don't worry about that. And so what does that mean graphically? Well, that means that so the first entry, the first pointer from U, which we'll call a jump pointer, is just to its parent. But then the next one is up 4 nodes away. So this is 1. No, the next one will be -1, -2 will be to there. The next one after that will be to there, and then the next one will be, 8 nodes that have a depth 8 less than that of U. Okay, so and you store that in an array. All right, and now when you give me a query, so first of all, so that's the whole structure. And I think you're convinced that this has space n log n because, well, there's n different nodes U. Each one has to store an array whose length is at most log n. So that's the space. And how do you answer queries? Well, you give me some query that has U and some value D, which is the depth of the ancestor that I want. And what I'll compute is a value delta, which is equal to the depth of U minus D. So how many levels up do you have to go to get to this thing? And now I look in this array for the element at index, what would be log base 2 of delta floor. And if you do that, what you'll find is a pointer to an ancestor of U, which takes you at least halfway to the answer. Right? So you take the longest, this is basically taking the longest jump pointer out of U, which does not take you too far. And since the jump pointers double in length, the longest one that doesn't take you too far takes you at least halfway. In fact, I guess it takes you always definitely more than half, strictly greater than halfway. All right, so then from U, I can do this to get to a node that's at least halfway. And now from that node, I can do the same thing to get me at least halfway again. From that node, I can do the same thing to get me at least halfway again. That will take at most log of delta steps. And delta is at most n minus 1. So there'll be at most log of n minus 1 steps before I get to this answer. Okay. All right. Easy stuff so far. Now, unfortunately, unlike range queries, we can't immediately turn this into something that works in only 2 steps. So there's a reason for that. The reason is in order to do that, we would have to solve basically have to solve the level ancestor problem again. But we're happy with that for now. Okay, and we'll remember the names of these things. We have table. This one is called jump pointers. Now let's not get too ambitious. Let's instead try and just shave a bit of space here, but not get the query time down so far. Is that the order I want to present it in? Yeah. Okay, good. So now this is what I want to do. And this requires a new idea, at least something we haven't seen yet in this class. And the idea, well, there's a couple of them that are needed. The first thing is the long path decomposition. So the way that works is you give me a tree. Well, let's work with this one as an example. And that tree has a particular height, which is the length of the longest path from the root to a leaf. So it's the maximum depth of any leaf. And well, we'll pick one of those leaves of maximum depth and look at the path to that leaf. So that thing there is called a long path. Abstractly, there's our tree. There's some long path. And hanging off that long path are subtrees. And if I take the long path away, so imagine that I erase all these nodes, then I'm left with a bunch of disconnected, a bunch of subtrees hanging off there. And I do a long path decomposition. So my long path decomposition consists of this path plus whatever paths I get when I decompose the subtrees. Okay. So the subtrees in this particular example is this node, which is all by itself, and whatever I get when I decompose this tree. So when I decompose this one, the longest path has length 0. It's a single node. And when I take it away, there's nothing left. So I'm done there. On this side, there's a path of length 2. Let's make it this one. And when I take it away, then there's 2 individual isolated nodes. So those are trees of size 1. And I decompose each of those to get something like this. Okay. So a long path decomposition is just, oh, I forgot this one as well, is just a partition of the nodes of the tree, and such that each set in your partition is corresponds to a vertical path in your tree. Well, that's what a path decomposition is. Long path decomposition is the one that you get by doing it this way, always taking the longest path from the root to a leaf. All right. So that's one, that's the tool that we'll need. Now, why is this a useful thing to do? Well, if your tree is just a path, then the level ancestor problem is easy, right? Because if your tree is a path, you could just do something like store the nodes in an array. Each node remembers its depth, which just is its position in the array. And then if you give me a node, like this node u, I know what the depth of u is, so I know where it is in this array. But well, even easier, I mean, you just give me d, the query depth, and I look at position d in this array. That's the ancestor of u at depth d. Okay. So solving it for a path is very easy. So how can we use that here? Well, it sounds like then we can do something like say, well, we'll solve it for this path, this first longest path that we made. So if you happen to give me a node, a query node u that is in this path, then I can tell you the answer for any depth. So those guys are done. If you happen to give me a node u that is in some other path, like here, and well, then you tell me so now u does need to remember its depth, its actual depth, and let's say position in this array, then either the answer you're looking for is going to be in this path, which you can know if you know the length of the array and the depth of u and its position in that array, or it's not going to be in this path. So the generic picture looks like this. Here's the path that contains u, and you're asking me about some ancestor whose depth is up here. In which case, well, u just needs to, well, we can reduce that to this problem of you take this node, its parent is in a different path. I don't know, maybe it looks something like this. So, from u we can, well, just look at the first element in the path that contains u, look at its parent, and then work from there. So that decreases the depth. So you might hope that this will eventually reach the thing you're looking for in log n steps. And if you hope that, well, that would just be wishful thinking because it's not true. We have to be a little bit more clever than that. And why is it not true? Well, because your tree could look like this. Start with a path of length root n. Give the root of that path a child. That child has a path of length root n minus 1. And the first node in that path has a child, which is a path of length root n minus 2, and so on. Now, all the leaves have the same depth. They're all at distance root n from the root. So if I do a long path decomposition, there is one of the longest, I mean, that's the longest path in the tree. So that might be the first thing I put in my decomposition. And then I'm supposed to recurse on all of the subtrees that I get when I take that away. But there's only one subtree. It's this one. And then, well, that could be the next thing that goes in the decomposition. Take that away. What's left is this thing. That could be the next thing that goes in the decomposition, and so on. until at the bottom here, there's a path of length 2, and then finally this thing by itself. Now, if I ask for the level ancestor of this node at depth 0, let's say, well, then that means the answer is not in the path that contains this node. So I have to go up to the parent of that thing, which is the first node in this path. But the answer is not in there. That's already the top node in that path. So I have to go up to the parent of that one, and so on. And so basically, the query just ends up walking along this path here, which has the same length as every other root to leaf path. It's of length square root n. So that doesn't work by itself. The only good thing so far about that is I think you believe, we should believe at least, that it uses O of n space. Why does it use O of n space? Well, because every node is in exactly one of these paths. So it's using like one array location. And in addition to that, every node has to remember its depth, which is just an integer, and a pointer to the, whatever it means to, a pointer to the head of the array, and maybe the depth of the node that's stored there. In fact, you don't even need that because this already stores it. So pointer to the array and needs to remember its own depth. That's enough. So it's O of n space, but it's got this awful square root n query time if you get a really bad tree. Well, here's a trick you can do. For each of these paths, so after you've done this long path decomposition, you do what's called, you're going to turn it into something called a ladder decomposition, which is not really any more complicated. All a ladder decomposition is you take each long path, you look at its length, and you grow it upwards by the same amount. Okay, so this one here goes upwards by that much. So, instead of that short path, you've got this one that goes up to here. And you may have to stop before you get to, before you make it twice as long, because you get to the root before that. So we can try and do that in this picture. This path can't be extended upwards. This path has one node in it, so when we extend it upwards, we'll get a path with two nodes in it. Same thing with this one. This one, when we extend it upwards, we should get 6 nodes, but we can only get as far as the root, so that's all we get there. And this one has 1 node, now it's going to have 2. This one has 1 node, now it's going to have 2. Okay. And yeah. All right, so I make each path at most twice as long. So now some nodes are in many of these paths, but you think of the node as belonging to the one, the long path that created it, not the ladder, not every ladder that it belongs to. So every node is in exactly one of these long orange paths, although it may be in many of these, what we call ladders, these yellow paths here. For instance, this node is in the first long path, but it's actually in 3 ladders, the one for the long path and these 2. So it only needs to remember which ladder it belongs to, not every single long path that it belongs to. Okay, why is that going to help? Well, so my claim is if you do that, then suddenly the query time drops from square root n down to log n. Well, just try and do one of these queries. So you start at u. It's in some long path. And so that long path has length at least 1. which means that at the very least, the ladder of U contains 2 nodes. So if we go up to the top of the ladder, use ladder, then we at least we get somewhere. Now that node is part of, well, there's 2 things to notice about that node. That node is part of a tree whose height is at least 1. Okay, right? From this node, the height of this node is the length of the longest path that starts at this node and goes to one of its descendant leaves. And I know that there's at least a path of length 1. And if your node is in a tree whose height is at least 1, that means its longest path has length at least 1. Right? So this belongs to something. The longest path whose length is at least 1, which means that its ladder, so its length is at least 1 and has at least 2 nodes, which means that the ladder that contains this node has at least 2 nodes above it. So the top of that ladder is a node whose height is at least 4. It belongs to some longest path whose length is which contains at least 4 nodes. I don't know, something like that, which means the top of its ladder is a node of height at least 8. So this means that, well, if you start at U and you just climb these ladders, you'll within log n steps, you'll reach a ladder that contains the node of depth d. In fact, within log n steps, you'll reach a ladder that contains the root. So somewhere along the way, you'll reach a ladder that contains the node whose depth you want. That makes sense? Yep. So to know what a ladder is, you have to know about this longest path decomposition. And now you take each path in that path decomposition and you extend it upwards by so that you double its length. You double the number of nodes in it. Now that doesn't really change the size because it's the same data structure, but you have twice as many elements now, nothing more. So it's still size stays O of n. But the difference now is when you walk to the top of a ladder, you get to a tree whose height is at least twice as much as the node you started at. Or you get to a node whose height is at least twice as much as the node you started at. Okay? Is that clear? Yeah.
For example, those 2 like ladders that 2 elements, say that you can't fit 4, so
You mean like so which one? So this one here, this was a long path that had 3 values in it. Here? So this one was a ladder of, I should stop saying length. I'll say that it has 4 nodes in it. And that means I would like to turn it into a ladder of length 8, but I already reached the root before I do that. In fact, this one contains the root. But for example, here is a long path with 3 nodes in it, which means I would like to extend it into a long path with 6 nodes in it, but I already reached the root before that. But in many cases, like all of these singleton ones, you'll be able to double the length of the path. And if you don't double the length of the path, it's just because you reached the root already. Okay. All right, so that is O of n, O of log n. And that's what we'll call ladders. So now something really clever happens. we can take these two structures and make them into something that has constant query time. Does anybody see how that? So if I compute both of these structures, then I will have space n log n because there's this big one here. But even though each of them has log n query time, by using both of them, I can get constant query time. Does anybody see how? Yep. I don't know how many ladders we have. We have as many ladders as there were long paths in the long path decomposition. And the exact number really depends on the shape of the tree. Let's see what we can do. And we can figure it out together. We get a query that starts at node U, and it's supposed to take us up to a node of depth D. We have a choice. We can either use the jump pointers. We can start by using the jump pointer structure, or we can start by using the ladder structure. Which one makes the most sense to use to start with first? The jump pointers. Why the jump pointers? Because the jump pointer from U, there's a jump pointer that takes us at least halfway. So in one step, we get to a node that takes us at least halfway. And what do you know about this node? So this node, well, more slowly, in the long path decomposition. So this is a path that contains this node and goes to the deepest leaf descendant of this node. So in particular, that leaf descendant is at least as deep as U. Okay. So this node has height at least as much as we've traveled so far, which was halfway, at least halfway, which means now it's in a ladder which contains at least those many nodes above it, and in particular, it contains this node of depth D. So you put these two things together, and even though each one has not great query time, suddenly the query time becomes constant. Just by starting with, well, I mean, doing the sort of natural thing, which is, start with the data structure that's going to take you the furthest to begin with, and then, well, then you do the same thing again, but in this case, you're guaranteed that the second structure will take you the rest of the way. Okay. So you can get O of n log n space constant query time, and this is jump pointers and ladders. They really should have somehow called these snakes. Somewhere snakes should have showed up in here. So we have the snakes and ladders solution. Okay, good. We're getting dangerously close now to an optimal data structure, because we're certainly not going to be able to do better than linear space and constant query time. So let's work towards solving that. In fact, it's a little bit weird because this structure is the combination of these two structures. One of these structures only uses linear space. This one, the jump pointer structure, is the annoying one. It's the bottleneck in terms of space. So this is where the bottleneck is. Well, we won't just store the large distances. We'll store, well, we've seen a technique twice now for sort of what we can do when we have a data structure that's too big. Yeah. Yeah, when we have a data structure whose space is too much, the sort of generic trick is just don't put all the data in it. So instead of putting all n pieces of data in it, only put n over log n pieces of data in it, and then it won't matter. We have to think about how we're going to apply that trick in this case. So a few little things to notice. Let's look at this jump pointer algorithm. You know, if I look at node U, it's got, well, a path up to the root. And it has all these jump pointers. Something like that. And if I look at the next node along that path, it has jump pointers. And if I look at the next one, it has these jump pointers. That would be this one. And then I'm very quickly going to run out of colors. I don't know, I probably did something wrong already. Anyway, I'm very quickly going to run out of colors here, but you see there's a giant mess of crossing edges happening here. That seems like a lot. Seems like way more than we need. In particular, let's erase all those. For some node up here on the path, if I think about what I wanted to do with that node is I wanted to take a step, somehow a step upwards in some sense. That's what I do with the jump pointers for that node. But actually, if the bottom node on the path has jump pointers, and this happens to be the node that I'm querying, so I'm doing something like the level ancestor of U, D, this is node U. Well, I could get that answer by starting down here and using, I mean, starting from this node. It would be the same answer, right? So call this thing U prime. These two things are the same. And what's the relationship between U and U prime? Well, the relationship is that U prime is a descendant of U. So if you, I mean, if you ask me a question about U, it's good enough if I can answer that question about any one of its descendants. Okay. Does that make sense? So that suggests that we really don't need to store a lot of jump pointers. There's a few nodes who will need their jump pointers. And then there are some others that they can just borrow them from their descendants. In fact, the obvious consequence of this, although it's not good enough yet, is that we only need jump pointers at the leaves. So all the leaves of our tree store jump pointers, and every other node just stores a pointer to any one of its leaves. That makes sense? Then we can still do that first step that we need to implement this thing, right? So you asked me a query about this node. I go to its representative leaf. From there, I take a step which is at least halfway to the depth I'm looking for from there. And then the ladder takes me the rest of the way. So we only need to store jump pointers at the leaves. Unfortunately, a tree can have a lot of leaves. That may not be, there may be half the nodes in our tree could be leaves. For instance, if it's a perfectly balanced binary tree, then actually strictly more than half the nodes are leaves. So that's not enough just to store these things at the leaves. But maybe we can do something which is to cut some things off of our tree, little trees.
Pat,
Yep.
I just have a small question.
Mm-hmm.
Why is it sufficient to have jump pointers only at the leaves?
Well, think about what we want to do for this combined algorithm. So you give me a node U, and I want to know its level ancestor at depth D. So if U has a pointer to any one of its leaves, let's say this one, then that leaf has a list of jump pointers. One of those will take us halfway to D, or to this depth. And then from that node, there will be a ladder that contains it, which takes us the rest of the way. So I can replace the query that involves U with the same query, same depth, but for any of its descendants. So that means if I have one at every leaf, then everybody here has at least one descendant, which has the jump pointers that we can use to run this algorithm. Does that make sense?
Yeah, thanks.
Good. All right. So then the plan is that we're going to take our big tree of size n and clip off some subtrees. And once we do that, we'll be left with a tree whose size is only about n over log n, which means that in particular, it has only at most n over log n leaves. And on this thing, we can use the combined structure. There's no problem, right? So for queries involving this thing, we use the combined structure. It only has n over log n, leaves, which means that this space now is n over log n times log n, but that's only n again. So just like before, we take the fat structure, that's this one, and we only use it on a smaller amount of data. So small enough that it then has linear size. Then we need to figure out what to do down here. We've still got to deal with the small trees. But this will already handle a lot of things. Like if you give me, if you give me a query node in this tree and a depth, then for sure I can just answer it. There's no problem there. If you give me a node in this tree, in one of these little trees, and you ask me about a depth which is less than the depth of the root of this tree, then there's also no problem because I can just use the root of this tree. Its parent is in the big tree, so that's called the macro tree, and then answer the query from from there. And so really the only issue are queries that are in these little trees that end also, and the answer is also in the little tree. But first, before we do that, let's see how we get this tree. So what we're going to do is say that we mark a node U if use subtree as at least, here comes a magic number, 1/4 log base 2 of n nodes in it. Okay, so two conditions. And every child of U is the root of a subtree with less than 1/4 log n nodes in it. Okay. So what does that look like? Well, that might say we mark a node U that looks like this, and we mark it because when we look at this subtree, we see bigger than or equal to 1/4 log n nodes. So satisfies the first condition. But if we look at its children, all we see are subtrees that can, each one of them contains less than 1/4 log n nodes. Okay. So that's a node that's the condition that we use for marking a node. That'll be a special node. So we do that, we identify all the nodes that have this property. And well, what can you tell me about that set of nodes that have this property? Is there ever one of those nodes that's marked and you look in its subtree and you see another marked node? No, that can't happen. Why can't it happen? Well, because the reason you mark this is because it has more than 1/4 log n nodes, but every one of its children has fewer than log n nodes. So if this were to happen, that means, well, just look at the path from this node to this other marked node. The second node on that path is a root of a subtree that contains this whole subtree. But this whole subtree already contains 1/4 log n nodes. Therefore, this one does. Therefore, you wouldn't have marked this node. So when I make this set of marked nodes, I get a picture like this, that no node is an ancestor, no marked node is an ancestor of any other marked node. Yeah? Good. So that means that if I look at those marked nodes, each one has a subtree, and those subtrees don't overlap. Because if the subtrees overlap, that could only be because one is contained in the other. So all the subtrees are disjoint. But each subtree has size bigger than 1/4 log n. And they're all different. But there's only n nodes in total. So if you think about that for a few seconds, you'll realize, oh, that means that the size of this thing, in fact, well, the number of marked nodes is less than or equal to 4n over log n. Right? Because each one uses up a quarter log n of the available nodes. And so as soon as I had more than 4n over log n of them, that would mean that I have more than n nodes, which is not the case. Yeah? Clear? All right. So this is looking good, right? I have this macro tree. It has at most 4n over log n nodes. I use this combined data structure on this thing, and I get something that uses only O of n space. And if I look at the stuff that's hanging off of here, so that doesn't cover everything, right? There's still these other subtrees hanging off of here. By the definition of a marked node, every one of those subtrees has size at most 1/4 log n. Okay, good. This is really looking hopeful now. And well, all I need to be able to do now, so every one of these nodes in this subtree, they remember their depth, and they also keep a pointer to the root of their subtree. That way, if you ask me for a query about one of these nodes, I can check if the query depth you're asking for is smaller than the depth of the root or larger. If it's smaller, then I can just answer that query by going to the parent of this subtree and using this, this macro tree structure. Otherwise, I'll have to figure out the answer based on this tree. All right. So and these things here, they're called micro trees. So for each micro tree, we use the table solution, the stupid solution we came up with first. Right? The subtree has size at most 1/4 log n. So the size of the table that it needs is O of log n squared. And it answers queries in constant time, which is what we need. So the queries up here we can answer in constant time. It's these ones that we still have to deal with. So for each micro tree, we use one of those tables. Problem, though, is that there can be tons of these micro trees. In fact, there can be like nearly n of them. So that's not great. So if we use log squared n per micro tree and we have n micro trees, then we get a solution that has n log squared n space. That's worse than we started with. What's the trick that we're going to use now? So we reached the same sort of situation last time when we were doing range minimum queries, where we got stuck with a problem of query ranges that are like really small ones, little blocks. We did the same thing. We used the quadratic space solution for those. And that somehow it worked out. And why is that? Yeah. So what we're going to do is now count the number of different kinds of subtrees we can have down here. Remember, these things are tiny. They're only of size of 1/4 log n. So what I would like to show you, and remember, I was a little bit careful when I talked about the table solution. I said, well, I want to make it so that it doesn't depend on the names of the nodes that you assign to this tree. Instead, it's going to give you, it's just going to do, let's say, a depth first search and give the nodes names that are entirely determined by the shape of the tree. Okay. So if there's two trees here that have the same shape, then they'll have the same depth first labeling, even though, I mean, they have the nodes themselves have different, I mean, in the big tree, a node here has a different name than the node here, but each one only has to remember its name and its depth first labeling of its own tree. Okay, so how many trees of size at most 1/4 log n are there? Sounds like a hard question. But let's look at a tree and use the trick that we know. We'll take the Euler tour. And each time that tour goes down an edge, we'll put a plus. Each time it goes up an edge, we'll put a minus. Okay. So if you give me a tree, that gives me a sequence of pluses and minuses. The length of that sequence, the number of things in that sequence, is exactly twice the number of edges in the tree, because you go down each edge once and you go up each edge once. The number of edges in the tree is exactly one less than the number of nodes in the tree. Okay, so I'm getting a sequence of pluses and minuses of length at most 1/4 log n. And if I want, I can even finish it to a sequence whose length is exactly 1/4 log n, just by putting some extra minuses, which is kind of like pretending that if the tree happened to be smaller, then you just put some extra minuses. It's kind of like you walked up out of the root, just so all the sequences have exactly the same length. Okay, so what? How does that help me count the trees? Well, let's write down this sequence of pluses and minuses. I'll try not to mess it up. Plus, plus, minus, plus, plus, minus, plus, minus, 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 plus, plus, minus, plus. That brings me to here, minus, minus. So forget about that tree now. Just look at this sequence. Well, so this sequence describes an Euler tour that starts at some tree, starts at the root. Let's see if we can draw the Euler tour. Well, sequence starts with a plus. So we know that the first thing this sequence does is go down. Then there's another plus, so we know it goes down again. So this node has a child. Then there's a minus. So a plus immediately followed by a minus, that means this node is a leaf. And the Euler tour returns back up to here. But now there's a plus, which means we go down from this node, which means it must have another child. That we've never seen before. Then it's another plus, which means this node has a child. Then it's a minus. We return to this node. But then it's a plus, which means this node has another child. Then it's minus, minus, minus. We're back up at the root. And now you can see what's happening. Plus, plus, minus, plus, minus, minus. And even if there were more minuses, we would, as soon as we see that final, the next minus, we know we're done. Somehow that's the end of the tree. Everything else is just padding with minuses. Okay, so from this sequence of pluses and minuses, which has length 1/4 log n, sorry, not 1/4 log n, 2 times 1/4 log n. So we can reconstruct a tree, which means that the number of different trees is not more than the number of different sequences. So that tells us that, well, I mean, number of sequences, and these are plus minus sequences of length 2 times 1/4 log n, which is 1/2 log n, is, well, that's 2 to the 1/2 log n, which is the square root of n. And that is bigger than or equal to the number of trees with at most 1/4 log n nodes. So the number of trees with at most 1/4 log n nodes is at most square root of n. So each so if we start building the structures for each of these possible trees, we only have to build square root n of them. Each one has size log n squared, so the total space for all of those structures is only square root n log n squared, which is actually much smaller than n. And now each node in one of these trees just needs to remember 2 things, or a couple of things. It needs to remember, well, the stuff that I said before, the root of the tree and its depth, but it needs to remember its number in the depth first order of this tree, and it needs to remember a pointer to the table, which has all the answers for trees that are shaped like this. So off to the side, we'll have a bunch of these tables, not very many of them, and many trees will end up sharing the same table just because there's more trees than there are possible tables. Okay. So that gives us, what do we have? O of n space up here. For all of this stuff, we have another O of n, just because we have potentially n nodes in here, and each one stores a constant number of things and pointers, plus off to the side, we have a square root n log n squared, which is also much smaller than n. So in total, that's O of n space. and constant query time. So put all of these beautiful ideas together in these clever ways, and you get something that has, well, that's optimal. So just a couple of notes about this. So again, there's a reference, I mean, that you can download the paper from the web page. This is a solution that was presented about 15 years after the original O of n space constant time query time solutions for this problem. And in that paper, they note that the original solution, well, the reason that they wanted to do this is that the original solution had some very large constants in it. And so it was O of n, but the constant in front of the n here was something big. And actually, the authors of the original paper had estimated it to be something like, I don't know, 2 to the 2 to the 120 or something. So the original solution was really not practical or usable. But this is. I mean, it seems like we're doing a lot here. It takes a while to explain. But once you start digging into this and seeing how you can implement it, it's all quite simple stuff. So it's not a big constant. This storing all the possible answers sounds difficult, but why? It's not a complicated thing to do. And in the end, you're just doing an array lookup to find the answer. That's not a slow thing. It's a fast operation. All right, so that's a good place to stop today. So there you go. Yep.
I'm just curious, where did the 1/4 and the 4 sorry, I mean, like from the design perspective, they decided on this number, so we found that.
So why did 1/4 n show up? It showed up, and it's weird because it shows up before we use it anywhere. But it shows up because in the end, you want, well, in the end, you're going to multiply by 2 because you double the number of edges in the tree in this Euler tour. So that's going to give you the half log n. And then you take that to the power, you raise 2 to that power of that number. So that gives you the square root n. Now, they didn't have to use square root n here. In fact, they could have used anything less than 1/2. So they used 1/4, but if they had used anything strictly less than 1/2, then you would get something which is, you know, the end here, instead of square root n log squared n, you get n to the 1 minus epsilon log squared n. And this epsilon is bigger than 0 as long as you took, instead of 1/4, you use something strictly less than a half. But I think they just like root n. It's a clean answer. It's also the answer that showed up in their previous paper on lowest common ancestors. So it's just convincingly far away from n, much smaller than n. That's all. And I'm sure when they're designing it, they said, let's make it a constant times log n, and then they saw what happens to that constant when you do this calculation and said, well, then 1/4 is a good answer for this thing. All right.